Okay, in function notation, if y equals f of x equals ax to the p, then f of x2 over x1 equals x2 over x1 to the p. And that then tells us in words that the y factor is equal to the p power of the x factor. If x changes by some constant factor, then y changes by a related constant factor. And that is sufficient if we can visualize those factors to construct a graph. And in particular, okay, we talk about, I like to use the doubling, and of course that has a natural application to exponential functions and an illuminating, I think, picture. It gives us an illuminating picture of an exponential function. In any case, f of 2x over f of x is the ratio of the y values when x doubles. And we can write that out very simply. And I like to write, okay, I don't just cancel out a's. I hate cancellation. It's frequently done inappropriately. For example, students will cancel the x with the x and go on merrily about their way without ever understanding that they have failed to apply the basic rules of algebra. Okay? In any case, we do this. I like to write a over a, and we know that a over a is 1, and there's no need to talk about cancellation. And also, we can factor out the 2 to the p here, and we get x over x to the p here. That's just 1. And we end up with just 2 to the p. Well, whether we do it this way or that, from here to here, we can take it in any sequence anybody might desire, but this reduces to this under this assumption. Now, if a student starts with this, just starts doing a graph where y triples when x doubles, or y quadruples when x doubles, or y decreases or changes by a factor of 0.6, 60%, so that the next y value is 60% of the previous. We can ask students, after a little bit of preparation, to construct graphs with those characteristics without ever mentioning power functions. Then we can say, okay, well, here's a little bit of algebra, either using function notation or just plain old y2 over y1 proportionalities. And we can say that any function that has this type of characteristic is a power function. And we can even say, although we haven't proven it, that the converse holds. If the y ratio is some number c, whenever the x ratio is some number d, with c and d are constant numbers, then we can conclude that y has to equal a power function for some power p. And I got a question mark here. Is this implication valid? And of course that requires some proof. So we would save that, but the whole idea that we got to actually prove the converse if we want to really claim this, and whether we decide to actually prove the converse or not, depending on the sophistication of our students and their ability, it's profitable to mention that we would need to prove the converse in order to use this as a complete characterization of power functions. Again, by this I mean the process where y increases by a certain factor whenever x doubles. Okay, so what do I think the advantages are? First of all, this doesn't require number sense, as I've alluded to, and it doesn't require the calculator, which is a big reason students have no number sense. And also, using this, I think it's possible that we can build number sense in a way that we can approach by scaling. Okay, scaling would tend to build number sense. And I'll talk about scaling, but by scaling I simply mean that if we know that a certain phenomenon has the characteristic that doubling x changes y by this factor, and we have an instance of that phenomenon, we can take any point on the curve and give it any coordinates, and we get a power function with a appropriate power. And then scaling the graph according to the coordinates of this point gives us a reasonable graph of that power function, which we can then verify by plugging the numbers into a calculator. That would be an appropriate use of the calculator. Okay, anyhow, and other advantages, we have a non-numerical basis for understanding proportionality and asymptotes, as I'll try to demonstrate on subsequent videos.